Adrian's and Joe. So, last week on Wednesday, I had the Chapter 5 quiz. The grades for that are up, but a bunch of people need to make it up, so I'm not handing it back yet. The Chapter 6 quiz will be on Wednesday. Also, the Chapter 6 homework is due on Wednesday the 15th. The Chapter 7 homework is due on Monday the 27th. The Chapter 7 quiz will be on Monday the 27th. Today will be the last lab. The remaining two lab periods on the 20th and the 27th are for makeups. The exam is scheduled for the 29th. Yeah. Last day of the semester. It's just on chapters 5, 6, and 7. I decided not to do a comprehensive exam. So the remaining two periods, the 20th and the 27th, are for makeups. And also, if you need to make up a quiz or a lab or something, I'm always available on Mondays and Wednesdays from 10 to 1. And then there's some time on Tuesdays and Thursdays as well. If you want to talk with me about it. Any other questions? Okay. You know what? Because I don't want to stop recording and skip those announcements. I'll just leave the dead space at the beginning and the recording and fix it later. Things work better when they come down. So we were discussing spherical mirrors. So a spherical mirror is a section of a sphere that's curved, has a radius r and a center of curvature c. And the geometry of a spherical mirror can be described using several terms. You could have the radius and the center of curvature for the entire sphere. When you're looking at a spherical mirror, you're looking along what's known as the principal axis, which is a line drawn through the center of curvature to the surface. And where the principal axis intersects the mirror's surface is known as the vertex. And the focal point is along the principal axis, one focal length away from the vertex. So here's a drawing of it. You have a sphere. Focal point is here. One focal length away from the center of the vertex. Here's the center of curvature. And the focal length equals half the radius. For a concave or converging mirror, you're looking at the inside surface of a spherical section. It's a recess or a cave. Incoming light rays that are parallel to the principal axis converge and pass through the focal point. Incoming light rays that are not parallel to the principal axis will converge on the focal plane. So here you have light rays converging, and they'll form across the focal plane from incoming rays not parallel to the principal plane. For a convex or diverging mirror, you're looking at the outside of the spherical section. So instead of bringing the light together, it spreads it out. Incoming rays that are parallel to the principal axis are reflected such they appear to diverge from the focal point. And non-parallel rays coming to the mirror get made parallel to the principal axis. This gives the viewer an expanded field of view. So parallel rays coming in look like they're coming from the focal point. And you can solve images formed by spherical mirrors using ray diagrams. We commonly use an arrow to represent the object that is being imaged. And the location, orientation, and size of the image can be determined by drawing two rays. The first ray gets drawn parallel to the principal axis and then gets reflected through the focal point. And the second ray is drawn through the center of curvature to the mirror's surface and gets reflected directly back. You can also draw a ray through the focal point that gets reflected back parallel. The intersection of these two rays is the position of the image. So you can see here, we have a parallel line that goes through the focal point, gets reflected, goes through the focal point, and a line to the center of curvature that meets. It's also possible to draw a line through the focal point that comes out parallel. So here's an example with an animation. This is doing one through the focal point that comes out parallel and a parallel line that goes through the focal point. But if you also draw a line to the center of curvature, you'll see it passes through the top there. If you have an object that is located between the focal point and the center of curvature, you will get a real image that is larger than the object, inverted, and further from the mirror than the object. If the object is the previous image here, this is what if the object is beyond the center of curvature, you get a real image that is inverted, smaller than the object and between the center of curvature and the focal point. And lastly, so here you can see the image. That is what's happening on the board right here. There's a concave mirror in the projector. You're seeing a real image. Real images can be projected on the screen. So a real image of the light source inside the projector. The image formed inside the projector. And the image formed inside the projector is upside down from what you're seeing here. And lastly, if you're inside the focal point, you get a virtual image that is larger than the object in question. If you've ever used a shaving mirror or one of those little dental mirrors to magnify something that you're looking at, that's what's going on here. So a shaving mirror, you're inside the focal length of the slight curvature. It allows you to see your face larger to get more control. Same thing with those little dental mirrors. When your dentist is looking at the back side of your tooth, they're looking in the dental mirror. The dental mirror is concave. It effectively magnifies your tooth. So here you get a virtual image on the far side of the mirror. The virtual image is upright. So just in general, real images will be on the same side of the mirror. They will be inverted. Virtual images will be on the far side of the mirror. They will be upright. So any image can be either real or virtual, upright or inverted, and larger and smaller than the object. And in general, unless you have more steps involved, but in this case, real images will be inverted and virtual images will be upright. That's the pattern you will see for this whole chapter. To get a real image that is upright or a virtual image that's inverted, you need more mirrors or more lenses. So you can see an example of a real image that is upright here, but there's two mirrors. So image characteristics get determined by several criteria: the object distance, the distance of the object from the vertex, the focal point, and the focal point or the focal length of the mirror, and the size and orientation of the object. And the distance of the image from the vertex is called the image distance. And it turns out there's a reasonably straightforward relationship between these. Real images are, so let's go over the types. Real images are images for which the light rays converge, so you can form an image on a screen. there is actually light at the location of a real image. Hence why they're on the near side of a mirror. Virtual images are images where the light rays diverge and cannot form on a screen. That's like the image behind a mirror that you see when you're looking at a flat mirror. That's a virtual image. So virtual images form behind or inside the mirror where the light rays appear to converge, and a virtual image results when the object is inside the focal point. Or if you have a convex mirror, the image is always virtual. So a concave, just a second, I forgot to do something. Should load. Come on. Okay, I think I have to close this and reopen it real quick. Sorry. There we go. There we go. So here is a video about
Mirage, an extraordinary optical toy, one of the best ever made. This little piggy went to market. Well, I think it's a pig. It looks pink, and I should be able to pick it up, but it's just not there. I'll try poking it. No, nothing there either. Of course, it's a mirage, for when I lift up the top parabolic mirror, there the piggy is really inside, quite real and quite solid. But when I replace the top parabolic mirror, there he is in a mirage form, looking as though he's standing on a little curved mirror. The mirage.
I have one of those right up here. Has a frog instead of a pig. And you can come up and look at it. So for a convex mirror, we can also draw ray diagrams. We use the same two rays through the line through the focal point, a line through the center of curvature, but we have to extend it through the mirror. And the image from a convex mirror is always virtual, upright, and smaller than the object. So we draw a line through the center of curvature, and we draw a parallel line that then gets deflected to the focal point. And the image is going to be virtual, smaller, and upright. So here's an example where an object is placed 25 centimeters in front of a concave mirror. If we construct the ray diagram with a center of curvature at 20 centimeters, therefore the focal length is 10 centimeters. If we construct the ray diagram, we will end up with a inverted real image here at we'll do the formula in a bit. So let me just quick it here. It's 16.7 centimeters. And here we have an object placed 15 centimeters in front of the same mirror. So it's closer, it's in between the center of curvature. And this one will end up with a larger image that is real inverted, and it's at 30 centimeters from oh, covered something. Okay, we're going to go. Name? Okay, I screwed up setting this up, but it's easy enough to fix. So here, an object is placed at a distance of 25 centimeters from a concave mirror or focal length 10 centimeters. Would you expect the image to be formed real or virtual, upright or inverted, or is it larger or smaller than the object? Well, this has a focal length of 10 centimeters, so the distance to its center of curvature is 20 centimeters. So we're beyond the focal point, we're beyond the center of curvature. We're beyond the focal point, so the image is going to be real and inverted. And we're beyond the center of curvature, so the image will be smaller than the object. So the image is real, inverted, and smaller than the object. Here we have an object of 15 centimeters from a concave mirror. Concave mirror with a focal length of 10 centimeters. Here, the focal length is 10 centimeters, therefore the center of curvature is at 20 centimeters. So we're in between the focal length and the center of curvature. We're beyond the focal length, so the image is going to be real, and therefore it will be inverted. And because we're in between the center of curvature and the focal length, the image will be larger than the object. It will look like this. We'll have a real inverted image that is larger than the object. So real, inverted, and larger than the object. And here we have an object 5 centimeters from a concave mirror, a focal length 10 centimeters. So is the image real or virtual, upright or inverted, larger or smaller than the object? Well, in this case, we're within the focal length. If you're within the focal length, the image will be virtual, upright, and for a concave mirror, larger than the object, like this. The image will be virtual, upright, and larger than the object. Now here we have a convex mirror. For a convex mirror, the answer to these questions are always the same. The image will always be virtual, upright, and smaller than the object. In this case, we're looking at one where it's 15 centimeters with a focal length of 10 centimeters. But the image will always be virtual, upright, and smaller than the object. So, turns out there's a nice formula for mirror. 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image. Focal length is positive for concave mirrors, negative for convex mirrors. DO is the distance from the mirror to the object, and DI is the distance from the mirror to the image. Negative DI is virtual image. So a negative pi is a virtual image on the far side of the mirror. Plus so that's sort of the conventions. And positive is on the same side of the mirror as the object, negative is on the far side. So if an object is placed at a distance of 3 centimeters from a concave mirror of focal length 2 centimeters, where does the image end up? I'll give you a couple minutes to do this. So 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image. So 1/2 equals 1/3 plus 1 over the distance to the image. 1/2 minus 1/3 is 1/6. That equals 1 over the distance to the image. So the distance to the image is 6 centimeters. And it's positive. So this image is real and 6 centimeters in front of the mirror. Any questions? Now, lenses consist of material that's plastic or glass that refracts or bends light waves to give an image of an object. There are 2 main kinds. Converging or convex lenses that are thicker at the center than the edges, and diverging or concave lenses that are thicker at the edges. Converging lenses are the equivalent of concave converging mirrors. Diverging lenses are the equivalent of convex diverging mirrors. So the concave convex thing switches between lenses and mirrors. Converging lenses are thicker in the center and thinner on the outside. Diverging lenses are thicker on the outside and thinner in the center. And rays parallel to the principal axis will converge at the focal point opposite the lens for a converging lens. And they will diverge as if they were coming from the focal point on the same side of the lens for a diverging lens. So for a converging lens, it brings the rays together to a focal point on the far side of the lens. For a diverging lens, rays through the parallel to the principal axis appear to diverge from a focal point on the incident side of the lens. So we can use basically the same procedure with ray diagrams to figure out where images will appear with lenses. Very similar to what we can do with mirrors. This is technically using what's known as the thin lens approximation, but as long as your lens isn't too thick, yeah, this works. So the location, orientation, and size of an image can be determined by drawing 2 rays. And in order to construct ray diagrams for lenses, only the focal points for the respective surfaces are needed to be known. So the first ray you draw parallel to the principal axis, and then it gets refracted by the lens through the focal point of the lens. And then the second ray is drawn through the center of the lens with no change in direction. And the tip of the arrow occurs where these two rays intersect, like so. You can also draw a line through the focal point of the lens on the far side that comes out parallel, and through the focal point on the near side that comes out parallel. So, if the object is beyond the focal length, an inverted real image is formed. The image becomes larger as the focal point is approached. If you are beyond twice the focal length, the image will be smaller than the object. If you are if you're between the focal point and twice the focal length, it will be larger than the object. It will get maximum size right at the focal point. Inside the focal point, the object will form a virtual image on the object side of the lens. So this forms an inverted real image. This is what you do if you're making an image with a lens, like in a projector. This forms a virtual image on the object side of the lens that is larger than the object. That's what a magnifying glass does. So with a magnifying glass, when you look at something through a magnifying glass, you hold the object you're looking at within the focal length, and so the object you're looking at appears larger. But this is what's going on say, like a camera. And then this is a virtual image on the object side. And for a diverging lens, the image is always upright and smaller than the object. So here we have a convex lens with a focal length of 12 centimeters. And we could draw ray diagrams for an object 18 centimeters from the lens. And you'll see you get a real image that is inverted. It's on the far side of the lens. And it is at 36 centimeters from the lens. Because it's within twice the focal length from the lens, so it gets bigger and further away. Here, we have a convex lens that has a focal length of 12 centimeters. Here we have an object 8 centimeters from the lens. So this object is within the focal length, so you get an image that is larger and virtual and on the same side of the lens. And what this image will be at minus 24 centimeters. So 24 centimeters from the lens, and it'll be 3 times as big as the initial object. So if an object is placed 25 centimeters from a converging lens of focal length 10 centimeters, is the image formed real or virtual? Is it upright or inverted? And is the image on the same side or the far side of the lens? So, to work this out, this object is beyond the focal point. That means you're going to get a real inverted image. And because it's a lens, it will be on the far side of the lens. So here, you can see the ray diagram. You get a real inverted image on the far side of the lens. And if it's 25 centimeters from a focal length of 10 centimeters, the image will be smaller than the object. But it's real, inverted, and far side of the lens. If you put an object 5 centimeters from a converging lens of focal length 10 centimeters, here is the diagram that I apparently messed up the animations on. Is the image formed real or virtual? It is virtual. It is upright, and it is on the same side of the lens. Virtual, upright, same side of the lens. Here we have an object placed at a distance of 25 centimeters from a diverging lens of focal length 10 centimeters. Was the image real or virtual? Is it upright or inverted? Or is it on the same side or the far side of the lens? Well, this is a diverging lens. For diverging lenses, the image is always virtual, upright, and on the same side of the lens as the object. The image is virtual, upright, and on the same side of the lens. And here are the ways you can draw it for it. So the lens formula. Oh, I'm going out. For the markers. There's 1 over focal length equals 1 over. Okay, this is not a very good marker. Oh, and this eraser needs cleaning too. Oh, yeah. 1 over focal length equals 1 over BO plus 1 over BI. Plus for converging, we go convex lenses minus for diverging. That's concave lenses. So positive and negative focal lengths switch between mirrors and lenses. For concave lenses are negative focal length, they're diverging. Concave mirrors are converging. But then the eye plus is real, far side. Lens minus is virtual. Same side. So that's the way it works. Positive is real, it's on the far side of the lens. Negative is virtual, on the near side of the lens. And this eraser needs I have like that. So if you have an object placed at a distance of 15 centimeters from a converging lens of focal length 10 centimeters, where is the image? So 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image. That's 10 centimeters equals 15 centimeters plus 1 over the distance to the image. So 10 centimeters, sorry, 1 over 10 minus 1 over 15, or 1 over 10 centimeters equals 1 over 15 centimeters plus 1 over DI. So we subtract 1/15 from 1/10 and we get 1/30. So DI equals 30 centimeters. That will be 30 centimeters on the far side of the lens, it will be inverted and real. The image is real, 30 centimeters from the lens on the side opposite the object, and it will be inverted. Now, the human eye contains a convex lens. So you use a converging convex lens to see every day. This convex lens focuses the entering light on an area on the back of your eye called the retina. Photoreceptors called rods and cones are located on the retina. Rods are more sensitive and are responsible for light and dark vision. Cones are responsible for color vision. You have 3 different types of cones. That's why there are 3 primary colors. The rods and cones on the retina are connected to the optic nerve that in turn sends signals to your brain. So the image on your eye, the back of your eye, is actually inverted. And you can actually, there are ways to tell this, but they involve poking yourself in the eyeball, so I wouldn't suggest doing them. But if you stimulate like the left side of your eye, you'll see something on the right side. So the human eye, even though the image focused on the retina is upside down, the brain will properly orient it. And since the distance to objects varies, the focal length of the lens must also vary. And so you have ciliary muscles in your eye. They can adjust the shape and focal length of the lens. Now, it might be that your ciliary muscles don't do the best job, or there's something wrong with it. Most people's vision is not perfect. So there's a number of common vision defects within the realm of normal. So the 2 most common are nearsightedness and farsightedness. Nearsightedness is the ability to see nearby objects clearly, but not distant objects. When you look at distant objects, if you're nearsighted, the image forms in front of the retina. This happens because basically your lens, when you're looking at something distant, can't get to the right shape. So glasses with divergent lenses can correct this common defect. So this could be a problem with the shape of your lens or a bunch of things. So basically what you do is you basically put a diverging lens in that effectively creates an image that you feed to your eye that is functionally further away. I mean, functionally closer. So it helps correct for that issue. Farsightedness is the opposite. You can see distant objects clearly, but not nearby objects. The image forms behind the retina. So glasses with convergent lenses correct this common defect by magnifying and showing an image that's further away. And this happens to be relatively common as you get older, because as you get older, the muscles, your ciliary muscles, get weaker, and they can't squeeze enough to focus on nearby objects. And your lens gets stiffer and things like that. And that's why older people often need reading glasses. But there's a lot of ways to correct this. You can have glasses, you can have LASIK surgery, which, there's a bunch of parts in your eye that focus. So if you change the shape of some of the outer layers, you can effectively build in glasses, things like that. And these days, we can even replace lenses in eyes. My parents had their lenses replaced. So the near point is the point closest to the eye where objects can be seen clearly, and a person's near point will change with age. So children can usually focus on objects as close as 10 centimeters, Young adults can focus on objects as close as 12 to 15 centimeters, and adults past 40 start having trouble focusing on objects any closer than 25 centimeters. As you get older, the lens becomes less deformable and therefore cannot focus as readily. It definitely happens. Okay, cover a little more. We were talking about lenses. The lens formula, the human eye. So we were talking about electromagnetic. Light is electromagnetic radiation. It is electromagnetic waves. The light waves are transverse electromagnetic waves that have both an electric and magnetic field vector. Because they are transverse waves, it is possible to polarize them. That means you can take these waves and you can line them up so they all have the same electric field vector. And the way you do that is there are various processes that will do this. You can get most light that you encounter will be unpolarized. Some of it will be partially polarized, and then some of it will be linearly polarized. Now, various physical processes will polarize things. For example, when light reflects off of surfaces, it tends to get more horizontally polarized. This is why polarized sunglasses are very effective against like road glare, because that reflected light is horizontally polarized and polarized sunglasses are vertically polarized. So polarization is the preferential orientation of the field vectors. It can be attained via several means. And one of the most common is the use of a polarizing film, or Polaroid. You've heard of the Polaroid company. They're called that because they used to make polarizing film. Then they moved on to make cameras. So here, I have some polarizers with polarizing film. Both of these are polarizing in the same direction. Actually, I can probably figure out what direction they're polarizing in. Give me a second. Okay, they're both vertically polarized. It only allows the component waves in a specific plane to pass. So this takes all the polarizing, the light that goes through it, and turns it vertically polarized. So if I put two in front, nothing really changes. But the vertical light passes through the first one and then continues to pass through the second one. And human eyes have no way to detect polarization. It's not true for all animals. There are animals that can detect polarization. I believe mantis shrimp can, but human eyes cannot. Now, one of the interesting things about polarized light is if you have this, it's possible to take, so now I have one that polarizes vertically and then one that polarizes horizontally. And if I cross them, you can see it blocks out all the light. If I cross them a little bit, it's dimmer. This effect is how liquid crystal displays work. Liquid crystal displays, like in your phone or in a screen, have two polarizers with a layer of liquid crystal which can twist polarization in between, and the amount of twist can be controlled electrically. But here is a short video about what polarization is.
What is polarization? Light bouncing off objects allows us to see them. Light is an oscillating electromagnetic wave. We see different frequencies of that oscillation as different colors. The electric field component of a light wave can oscillate in any direction perpendicular to the direction of travel. Light from the sun oscillates in all directions. We say it is unpolarized. If the waves have a preferred direction of oscillation, they are polarized. For example, light from your phone is vertically polarized. Your polarized sunglasses are a polarized filter. Here, they let vertical polarization through. If we rotate them, almost all the polarized light gets blocked. Light produced by a torch is unpolarized. When we place a polarized filter in between, the light becomes polarized. In space, randomly moving hot gas or plasma emits unpolarized light, like the torch. Plasma threaded by a magnetic field is ordered and the emitted light is polarized. The magnetic field acts as a polarized filter. The strong gravity near a black hole bends the magnetic field and twists the polarization direction of the light from the surrounding plasma. The polarized light rays that manage to escape travel to a distant camera. The intensity of the light rays and their direction are what we observe with the Event Horizon Telescope. Using this knowledge, we can map out the magnetic fields that surround black holes.
And if you want to see an image of a black hole and the polarization of the light coming from it, you can look that up at the Event Horizon Telescope. They've managed to image the black hole in the center of M87 and also the black hole in the center of our own galaxy. So a polarizer is basically a bunch of slots that only allow the light to go in one direction. If you have two parallel polarizers, light will just pass through. Well, the first polarizer will polarize the light, get rid of half of it, but it will be transmitted through the second polarizer just fine. But if the second polarizer is at right angles, it will block the light. So here's a short video about another short video about the polarization.
Now, you might be wondering, is light a transverse or a longitudinal wave? How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.
So the polarization of light acts as experimental proof that light is a transverse wave, because longitudinal waves like sound cannot be polarized. Because they're moving back and forth in the direction of movement, there's no way to polarize them. There is no polarized sound. Polarizing sunglasses use the fact that light gets polarized by reflection. So light reflecting from the surface of the ground or water gets partially polarized horizontally. And these polarized reflections increase the intensity and is seen as an annoying or dangerous glare. And polarizing sunglasses are oriented vertically, therefore do not allow this horizontal component of light to pass, and therefore significantly reduce glare. So And LCD screens use the fact that you can rotate polarization to create images. So here, and that is why your phone is polarized, because it uses polarization of light to control how much
LCD
light
screens are
comes out.
cool. But how do they work?
Liquid crystal displays, or LCD screens, are composed of millions of pixels which are made out of 3 smaller subpixels, each in control of one color, red, green, or blue. By changing the value of each subpixel, any color can be displayed. An LCD screen is made out of the backlight, horizontal and vertical polarizers, transparent electrodes, liquid crystals, and a screen, all working together so you can watch your favorite shows. The backlight emits both horizontal and vertical polarizing light, which passes through a filter, filtering only horizontal polarizing light. Now, as the name suggests, they use liquid crystals in order to change the value of every single subpixel. Depending on the color required, transparent electrodes will align liquid crystals to alter the filtered light, allowing it to pass through the second filter. The double filtered light finally hits the screen, producing a value for the subpixel. This value increases depending on how much light it receives, scaling from 0 to 255. This means that every pixel is controlled individually, making for precise displays.
LCD screens are truly incredible and fascinating. Thank you for watching.
That's basically how LCD screens work. Though modern LCD screens don't go between 0 and 90 degrees, they go between like 180 and 270 degrees. Just turns out more rotations was more efficient somehow. You could use less power, so it saved energy. Additionally, light interferes with itself and will spread out when it moves past a opening or obstacle that has a size smaller than or equal to the wavelength. This is diffraction. You experience this in the lab where we had a diffraction grating and we sent, let me get the more obvious one. Light through it and it separated it out, like you can see here with this laser. So all waves, sound, light, water, etc., will show diffraction. You can see this easily in water waves as they bend around obstacles. It's also why you can hear sound around corners. And the larger the wavelength compared to the size of the opening or object, the greater the diffraction. So sound waves easily bend around corners, while light waves, which are much smaller, don't. So you can hear around corners, but you can't really see around corners. So here's an example of diffraction in water. You can see with a bigger gap, there's less diffraction. When it's closer to the wavelength length, you get more. So audible sound waves have wavelengths in the centimeter to meter range, while visible light has wavelengths around 400 to 700 nanometers. So you get noticeable diffraction that readily occurs for sound waves because objects are around that scale. We can hear sounds around the corner. On the other hand, a beam of light on an object casts a sharp shadow, as you can see here, with sharp boundaries. Because the wavelength of light is so much smaller than that of sound. You know what, we'll go into that in more detail next time. But yeah. So we were here. Okay, I will just save, stop sharing.